My name is Ruo-Chun. This is a joint work with Paul, Florian, Aristides, and Gionis. The problem of maximizing the Rayleigh quotient over a feasible set is of fundamental interest to many applications. One often solves this kind of problem using the top-eigenvector, but might fail to notice that what we use in practice is the approximative vector found by some numerical solvers. So to address this issue, we define the metric as the multiply gap introduced by numerical solvers, and we focus on the memory limited and path limited setting. However, all the prior analysis of R under the setting we consider are additive, limited to positive semi-definite matrices, and require at least as the order of log n passes to be meaningful. So this leads to the question of whether such a requirement is necessary or an artifact of analysis. And we confirm that it is an artifact by improving the analysis of randomized SVD. Our first result for positive semi-definite matrices provides the first non-trivial guarantee in the regime of sub-logarithmic passes and recovers the state-of-the-art result. Our core argument is the reduction from the value of R achieved by randomized SVD to the problem of estimating the projection length onto a random subspace. The latter is well known in high-dimensional probability, and it follows from the concentration phenomenon of extreme singular values of Gaussian random matrices. Our first result is actually tight up to a constant factor, and beyond the worst case, we provide a lower bound sensitive to spectron decay, and in some cases, we can even have a constant guarantee with a single path. And our second contribution is that after introducing one assumption on the negative eigenvalues, we get the first non-trivial guarantee for indefinite matrices. And finally, we propose an extension motivated by asking that suppose that we know the projection length of the top eigenvector onto a constant vector is large, can we design a better algorithm by changing the random matrix? And our answer is yes, by using Bernoulli random matrix. So our last contribution is that we study the property of Bernoulli random projection and demonstrate its usefulness when such prior knowledge is valid both in theory and in experiments. We'd like to conclude by mentioning that it is an open problem to characterize the fundamental limit of R under the path limited and memory limited setting. And it will be interesting to extend our results to other settings such as stochastic matrix or top K eigenvector approximations.